Hello there, fellow math enthusiasts. Mrs. Delzati here. Today we're going to be working with polynomial functions. We're going to work to identify the degree and the type of the function. We're also going to be able to determine the end behavior of a graph. So first of all, our polynomial function, when we talk about it being in standard form, it is always written in descending order, meaning our biggest exponent comes first and then we work our way down to the smallest exponent. Now, when we're talking about our polynomial functions, we can go ahead and we can figure out what type they are based on the degree. If we have a degree of 0, meaning that we have an x to the 0 power, which we typically don't see, we normally just see a number, we're going to end up seeing that this is called a constant. When we have a degree of 1, something like 5x plus 1, this is a linear function. We've spent a couple units dealing with degree 2. Degree 2 is a quadratic. Degree 3, x cubed, is going to be a cubic. Degree 4, when 4 is the biggest exponent that we see, that is going to be our quartic. And a degree of 5, when 5 is the biggest exponent that we see, that is going to be a quintic. Now, the other degrees, as we go bigger, they do have types as well. We just don't focus on those as much, though. So when we want to figure out if a function is a polynomial function or not, two things need to hold true. First of all the exponents, they need to be whole numbers. That means there's no fractions. There's no decimals. There are no negative numbers. And that is in our exponents. All coefficients also need to be real numbers, which means we don't have any imaginary numbers. So as we take a look at number 1, I want to decide whether the function is a polynomial function. If it is, I want to write it in standard form. I'd like its degree, its type, and its leading coefficient. And if not, I want to be able to explain why not. So as we take a look at A, f of x is equal to 2x squared minus x to the negative second. Now I see that this exponent here is a negative 2. Since all exponents need to be whole numbers, we can say that this is not a polynomial function. So we're going to say no. And our reason for that is because we have a negative exponent. Now looking at B, I have negative 0.8x cubed plus x to the 4th minus 5. I do see that my exponents, they are whole numbers. I do see all real coefficients as well. So therefore we can say yes, this is going to be a polynomial function. Writing it in standard form, I've got f of x is equal to, well, the biggest exponent that I see is my x to the 4th. And then I have minus 0.8x cubed, and then minus 5. Now, as I'm looking at this, I can see that the degree is going to be 4, which means it is going to be a quartic for the type. And then the leading coefficient, that's just the number in front of my biggest term. My leading coefficient is going to be 1. Now, when we're dealing with evaluating a polynomial function, we can go ahead, we can do this several different ways. The first way is to go ahead to put it into your calculator as an expression and use function notation. We can evaluate y1 of whatever the number is. Another way is to again put it into y1 and trace it on the graph. And a third way is to put it into y1 and set the table equal to ask and then put the number in. Personally, I think it's easiest to do this first method, which is to go ahead and use our function notation. So as we go ahead and we take a look at number 2, if I give you the function 3x to the 5th minus x to the 4th minus 5x plus 10, and I want to evaluate x is equal to negative 2. Well, I'm going to take this equation, I'm going to put it into y1, and then I'm going to evaluate y1 of negative 2. Let's see how that's done. So into y equals, I have 3x to the 5th minus x to the 4th minus 5x and then plus 10. I'm going to go back to my home screen, and I want to evaluate now y1 of negative 2. So I'm going to click my variables key. I'm going over to y variables, getting function, and then into y1, and then I want of negative 2. And when I do that, I should see that I get a negative 92. This is us being able to go ahead and to evaluate a function here. Now if we go ahead and we flip it over, we're going to again review our end behavior of a polynomial. End behavior refers to what happens to the function as x approaches both positive infinity and negative infinity. And we're going to see that based on the degree of the function and the sign of the leading coefficient, that's going to tell us everything that we need to know about the end behavior. So I have this broken up into two sections for us, when the degree is even versus when the degree is odd. I also have it broken up into two sections going this way, when the leading coefficient is positive versus when the leading coefficient is negative. If we think about degree being even and a leading coefficient being positive, think about a positive quadratic. All right, that is an even degree, that is a leading coefficient that is positive. If we think about a positive quadratic, it looks something like this. All right, when the degree is even and the leading coefficient is positive, it's going to follow what a positive quadratic does. It can go ahead, it can bump up and down as much as we would like it to in the center. But in the end, the ends are going to go ahead and follow what a positive quadratic function will do. Even and positive leading coefficient. So that shows that if x approaches positive infinity, notice that the graph is going up there, that means f of x is going to go ahead and approach positive infinity as well. As x approaches negative infinity, meaning it gets smaller and smaller, f of x is going to approach positive infinity as well. It goes up at the ends. Now if we have degree being even, but now the leading coefficient is negative, that's going to go ahead, that's going to follow a negative quadratic. It can go ahead, it can bump up and down as much as it wants in the inside there, but in the end it's going to follow what a negative quadratic does, even and negative. So as x approaches positive infinity, the graph is going down. That means f of x approaches negative infinity. And as x approaches negative infinity, the graph is going down. F of x approaches negative infinity. Now let's go ahead, let's switch to the degree being odd. Think x to the first power. That's a linear function. When the leading coefficient is positive, it's kind of like a positive sloped line. It can go ahead, it can bump up and down as much as it wants in the center, but in the ends are going to follow what a positive sloped line does. So as x approaches positive infinity, f of x goes ahead and approaches positive infinity. And as x approaches negative infinity, the graph goes down, f of x approaches negative infinity. Now again, if the degree is odd, think about a line, but now the leading coefficient is negative. Think about a negative sloped line. Going to follow something like that. The graph can go ahead, it can bounce up and down as much as it wants in the middle, but in the end it's going to go ahead, it's going to follow what a negative sloped line does. So as x approaches positive infinity, f of x is going to go ahead and it approaches negative infinity since it's going down. As x approaches negative infinity, f of x approaches positive infinity since it's heading up there. So as we take a look at number 3, if I want to be able to describe this end behavior, the thing I'm focusing on is the degree and the leading coefficient. Looking at f of x is equal to x to the 4th minus 4x squared plus x, I see that I have an even degree and the leading coefficient is positive, which means it's going to go ahead, it's going to follow what the positive quadratic does. Now, sometimes you may see that we write as x approaches positive infinity first. Sometimes it might be as x approaches negative infinity first. It does not make a difference. I'm going to do the positive one first as x approaches positive infinity. I do see that it's moving up at the end. So f of x is going to go ahead and approach positive infinity as well. As x approaches negative infinity, Well, f of x is going to go ahead and it's going to approach positive infinity too because it's heading up on the ends. As I take a look at b, I see a negative x cubed. Negative and then odd means it's going to go ahead, it's going to follow the negative sloped line, which means as x approaches positive infinity, f of x, it's going down, approaches negative infinity. And as x approaches negative infinity, it's going up there, f of x approaches positive infinity. All right, now the last thing that we're going to go ahead and review is being able to graph the polynomial, describe the end behavior, and making sure that we can find all of those good points on our graph. I'm going to go ahead, I'm going to do the end behavior right off the bat here. I know that since it is negative and it is odd, then as x approaches positive infinity, f of x is going to be going down, so it's going to approach negative infinity. And as x approaches negative infinity, it's going to be going up, so f of x is going to go ahead and approach positive infinity. Let's go ahead, let's put this equation into our graph here. Now let's graph it. I have negative x to the third minus 3x squared plus x minus 2. All right, and I can go ahead, I can see that I had my end behavior done correctly. Now I'm going to go ahead, I'm going to sketch this graph. And I see that it looks something like this, where I want to be able to find my x-intercept, my y-intercept, my local max, and my local min. I'm going to find my y-intercept first. I can do that by taking a look at my table. When x is 0, y is negative 2. So I have the point 0, negative 2. I want to make sure I make this big enough and stretch it out completely so I can get all the good stuff on that graph. I also want my x-intercept. I'm going to do second trace. That is my 0. I'm going to arrow so I am on the left of it. Click enter. And I'm going to arrow, come on back down. So I'm on the right of it and click enter. And then I'll take a guess. And I see that I am at negative 3.457. This right here is just having some rounding error. That means 0. So I have negative 3.457, 0. And now I want to be able to find my turning points. I want to find my local max and my local min. So second trace, I'm going to do the minimum first. I'm going to arrow so I'm on the left of it. I'm going to arrow so I'm on the right of it. And I'm going to go ahead, take a guess. And I see that I have negative 2.155. And then my y-coordinate is at negative 8.079. Now, looking to figure out what my maximum is, it looks like my y-intercept and my maximum, it could be the same thing. You always want to make sure that you check though, okay? Because a lot of times they are different. So second trace, I'm looking for my maximum. I'm going to arrow so I'm on the left side of it. I'm going to arrow so I'm on the right side of it. I'm going to take a guess, and I do see that they were not the exact same point, that this was 0.155 and then negative 1.921. So this was just a quick introduction to our polynomial functions, being able to understand the degree and the type, reviewing end behavior, and then being able to find all the good stuff on our graphs. Del Zadi is done for today. I will see you in class.